In this new section, we're going to be talking about homogeneous, try to break that down legible, homogeneous linear equations with constant coefficients. Let's look at a second order homogeneous linear equation with constant coefficients. You can have a constant times y double prime. That's what made it linear, where a is not 0. That's what made it second order, excuse me. Plus a constant times y prime. That constant could be 0. Plus the constant times y. Over here, I think I said a constant times y. Of course I meant a constant times y prime. Plus c times y, constant times y. I'm making it homogeneous. That's the second order equation of the type that we're going to be working on. The coefficients of y double prime, y prime, y triple prime, y to the fourth prime, etc. are all constants. Constant, constant, constant. Now, I claim that a solution would be in this form, e to the mx. Now that's going to make life easier because when I substitute, well, you'll see in a moment what happens when I substitute that solution in here. So I know how to write y. Of course I know how to write c, but I don't know how to write y prime yet. So I take the derivative of y, and I get m e to the mx. And I multiply that by b with no problem. So now I need y double prime. To get y double prime, you don't take any second derivatives. You take the derivative, you take a derivative of y prime. And you'll get m squared e to the mx. Now, you substitute this into our equation. I'm even going to put a star here. So when I talk about the star equation, I mean that one. So it's a times y double prime. I'm just reading that equation. And then I realize I can write y prime this way. Plus b times y prime. And that's how I can write y prime. Plus c times y. And this is how I can write y equals 0. Now when I look at this equation, at least the left side of it, these are the terms. It's a times m squared times e to the mx, b times m times e to the mx, e times e to the mx. They all have an e to the mx term. So I write that down, and then from beginning to end, I write down everything except what I put this curly line under. That is am squared plus bm plus c, and it equals 0. Now, e to any power is always positive. You just look at the e to the x graph. It's always positive. Okay? I mean, mx is going to be some number. And e to any number this graph is saying is always positive. And if you multiply two quantities and you get 0, one of the two factors must be 0. And it isn't this one. So it must be that am squared plus bm plus c equals 0. And this is the equation that we got from equation star. This is called the auxiliary equation for equation star. Now, how can we have gotten there a little bit more quickly? Let's just get rid of our side work and let's look at how we can get there quickly. Let's even put it up higher. Well, you have A, and since you have two primes, you have n to the second, you have a plus, you have B. Since you have one prime, you have an understood n to the 1. You don't have to write the 1. And then you have a plus sign and a C, and then Y really means 0 derivative. So maybe we should have n to the 0. But what is C m to the 0? Well, it's C times n to the 0. C times, n to the 0 is 1, and C times 1 is C. And that's just what I have. And don't forget to put equal and 0. So you can read off the auxiliary equation fairly easily. And this is true even if it isn't second order. If it's fifth order, it's not going to make any difference. If you have a fifth order, you have 3y to the fifth plus 2y double prime minus 3y prime plus 7 is 0. So this will be 3m to the fifth plus 2m squared minus 3m, let's say plus 7y, excuse me, plus 7 is equal to 0. For the record, if we had plus 7, it wouldn't be a homogeneous equation if this were plus 7. Because if we brought this 7 over, the right side will not be 0. Now, let's go back to our second order equation. To solve this auxiliary equation, this one right here, is a quadratic equation in M. Remember that the solution to this second order differential equation is y equals e to the mx. So we're going to solve this and solve for m and put that value of m right there. And if we have two m's, like m1 and m2, and if the m's are different, these two quantities are independent. So we can take a linear combination of them. Now, when you solve a quadratic equation, you get three different cases. You get three different cases. I'm not going to review why they're different. That's for a low-level algebra class. But if what's underneath the radical is positive, that means you have two distinct, that is different, real roots or solutions. Case 2. If what's underneath the radical in the quadratic formula, x is negative b plus or minus the square root of b squared minus 4ac, the whole thing over twice a. This is what's under the radical. And if it equals 0, that means you have one real root. And case 3 is actually going to be similar to case 1. If what's under the radical is negative, you'll have two distinct roots, but they'll be complex. Two distinct complex conjugate roots. The complex roots of a quadratic equation are conjugates. If you look at the formula, you should be able to argue to yourself why they'll be conjugates. Like 3 plus 4i and 3 minus 4i. These are conjugate numbers. And since they're complex numbers, we call them complex conjugate numbers. Okay. So now, the question is, how do we handle each case? We now know what 3 cases we can come up with. So let's look at case 1. So we get 2 distinct real roots. If m1 and m2 are the 2 roots from the auxiliary equation, then e to the m1x and e to the m2x are 2 independent solutions to their equation. Which equation? Ay double prime plus by prime plus cy is equal to 0. I'll show in a moment why they're independent, but for right now assume they are. That means we take a multiple of the first solution and a multiple of the second solution and add them together. That will be our general solution. Now, why are these independent? Because if they weren't, that would mean a multiple of the first root or the first solution would equal to the second solution, a constant multiple. Well, I can solve for k. I just divide each side by what k is being multiplied by. And this tells me that k, a pure constant, a real number, is equal to this. But this is not a real number. As long as m1 and m2 are different. And remember, in case 1, you had 2 distinct roots. The m1 and m2 are different. This is not a constant. This is a function of x. It changes. This will change depending on x. So, this really was not a constant. I tried to make it work, but it didn't. I said, well, a constant times e to the m1x is equal to e to the m2x. And I found out that that couldn't be. That could not be. It turns out that that constant, or that k, would be a non-constant value. So that is the solution for case 1, when you have 2 distinct solutions. And of course, I want what's on the top half of the board. I'm going to stay on this page. For case 2, when what's under the radical sign is 0, you have one real root. Suppose n is the real root. Call it m1. Well then, the general solution will be y is equal to e to the m1x is one solution, c1 times that, plus not e to the m1x, but x times that, times c2. That will be a second solution. And since they are independent, means you can't multiply e to the m1x by something, by a constant, and get back x times e to the m1x. The only thing that can go into that box is x. Yeah. x e to the m1x, yeah, that equals x e to the m1x. That's not a constant. Okay, this is one solution, this is the second one, and I'm taking a linear combination. But I can only really do that if these two are independent. And I showed below that they are. What you need to multiply this by, this solution by, to get the other solution must be x. And it's not a constant. X changes. So that's what happened with case 2. Now, we're going to go on to case number 3. That one's a little bit more involved, and I'll use a whole new page. Remember, for case 3, you get two complex solutions. So, if m1 and m2 are two distinct complex roots, then we have that m1, since it's a complex number, is a times bi. And m2 being complex is going to be a minus bi. Okay, so the general solution will be y is equal to some multiple of e to the m1x, but that's how I write m1, plus some multiple of e to the m2x. But this is how I write m2. And this is correct, but we don't want to write it that way. You should recall that e to the I theta is cosine of theta plus I times the sine of theta. So e to the I anything is cosine of the anything plus I times the sine of the anything. So e to the IB, this will be cosine B plus I times sine of B. And e to the negative IB, if it makes you happier, it's e to the I times negative B. So we're going to get cosine of negative B plus I times the sine of negative B. But you should remember that the cosine of the negative angle is just the cosine of the angle. That is, this piece here is just cosine of B. You should also remember that the sine of the negative angle is equal to the sine of the angle, but the minus comes in front. This minus is going to come in front. It becomes minus I times the sine of beta. I'm going to write that right above. The cosine of beta plus I sine of, minus I sine of beta. Now, I'm going to write these two equations I'm going to say on another page, but I'm going to put them up here. I'm going to put them up here. Now, if I were to add these two equations in the blue, on the left side, I will get e to the I beta plus e to the negative IB. And on the right side, well, when I add this and that, I will get 2 cosine B. And when I add this and that, I'd get 0. Likewise, if I were to subtract those two, well, cosine beta minus cosine beta is 0. You have plus I sine B, and you take away this, which is negative I sine B, you get 2 I sine beta. Because you can change subtraction to addition and change the sign of the second term. And since these are exactly the same, don't care whether you like how they look or not, if you add things that are exactly the same, you get 2 of those same things. So this becomes 2I sine beta. Now, let me erase this, please. At some point, we said that for case 3, that a general solution was y is c1e to the a plus bix plus c2 times e to the a minus bix. And this is for any values of c1 and c2. For any values of c1 and c2. Well, what if I let c1 equals c2 be 1, and another time I let c1 be 1, but c2 be negative? So let us look at this case for right now. So c1 and c2 are 1. That is copying this, except c1 is 1 and c2 is 1. I get y is equal to a plus bix plus e to the a minus bix. We can do a little algebra. This is e to the ax times e to the ibx. And distribute that. Plus e to the ax times e to the negative bix. Well, they both terms have e to the ax in it. So I can factor it out. E to the ax times e to the ibx plus e to the negative ibx. So it's e to the ax, this part, times this part. But this part is on top. This part is on top. It's 2 cosine beta. Now, this part is on top. So we'll just bring in the 2 in front. I get 2e to the ax cosine bx, it should be bx. So that's when I did this. Well, now what if c1 is still 1, but c2 is negative 1? That means this would just be negative. And the line below would be negative. Follow it through. Make sure you believe that. And then when I factor out the e to the ax, that will be negative. And there's e to the ax at the far bottom right here. That's this times this. But this is on top. It's right here. It's 2i sine bx. Maybe here I should just have x's. Maybe here I should have x. Okay? Alright. So now I'm saying, so we had when C1 was equal to C2 was equal to 1, what I had was that y, call it y1, was e to the alpha x times 2 cosine beta x. 2 cosine beta x. And I put the 2 in the front. And y2 is this here. But I'll put the 2i in the front. Now, those are two solutions to the differential equation where the roots were complex. Now, nonetheless, it's still linear. That is, when I plug this in, right here, in here, I'm going to have a factor of 2i. And when I take the derivative, the 2i just stays there. And after all, when you take the derivative of 7 times x squared plus 4x plus 1, if you were asked to find the derivative of that, this 7 stays. And it gets multiplied by the derivative of x squared plus 4x plus 1. 2x plus 4 if I'm not mistaken. And when you take the second derivative, that was y, that's y prime. When you take the second derivative, the 7 stays there. Okay, the 7 just stays there. Like it had nowhere else to go. And you multiply that by the derivative of this, which is just 2. Okay, the 2i factors out. That is, if you didn't have the 2i, what remains will still be a solution. Because you're going to have 2i times something, and it's going to be 0. Well, it must be this that's the 0. You can just plug in e to the ax times sine bx. Same argument with the 2. You don't need that 2. A general solution to the second order homogeneous linear equation is going to be the following. The general solution is going to be y is equal to a multiple of y1 plus a multiple of y2. The last thing I would do is factor out what's common. It's going to be that times everything but that. Literally, everything that wasn't common. C1 cosine bx plus C2 sine bx. That is the general solution of our second order homogeneous linear equation with constant coefficient. This here is the solution to this equation. If b squared minus 4ac is less than 0. If you have this equation, then what's right above is the general solution. You want to memorize that? Not such a bad idea. So again, if you have this equation and and b squared minus 4ac is less than 0, then there's your solution. Then there's your solution. Where do you get the a's and where do you get the alpha and the beta from? Find the roots. If the root to this equation is alpha plus or minus beta I, well, now you have the alpha and the beta. You have the alpha and you have the beta. Okay, a lot of theory. Now let's go and crank out some problems. Suppose you were given 6y double prime plus 7y prime minus 3y is equal to 0. First thing you should do is write down the auxiliary equation, which will be 6, that's double prime, so it's n squared, plus 7, that's 1 prime, so it'll be n to the 1, minus, that's 0 prime, so it's just minus 3, equals 0. Okay, now, this is not an algebra class. Not going to teach how to factor. But if you were to factor this, you would get 3m minus 1 times 2m plus 3. And this will equal 0. Well, if 3m minus 1 is 0, well then that must be 1. 1 minus 1 is 0. Because 3m is 1. Divide by 3, m is 1/3. Or 2m plus 3 is 0. You need to know how to what additive inverses are. This must be negative 3, because when you add 3, then you'll get 0. 2m is negative 3. Dividing by 2, m is negative 3/2. So in this case, although we never really computed the discriminant, we got 2 real roots. That's case 1. So the general solution will be y is equal to, remember, we're saying that a solution to this is y is equal to e to the mx. That's how we're getting this equation. These m's is that m. So it's e to the 1/3 x, that's one solution, and e to the negative 3/2 x, that's another solution. And they're not multiples of one another. You can't multiply this by 7 and get that. Okay, so fortunately I have to rewrite them. And then you take a linear combination of them, since they're independent. Take a multiple of the first one plus a multiple of the second. And there is your general solution. When you get 2, it's really not even differential equation. To go from here to the auxiliary equation should be simple. Factoring, that's all algebra, not differential equations. And then, for some off-the-wall strange reason, you then have to take these answers and put them up in the power with x next to it. And you have to memorize them. Okay, let's try another one. Suppose you had 2y double prime plus 3y prime minus 2 is 0. So it's going to be 2m, second derivative, second power. plus 3m, first derivative, first power. But you don't have to write the first power. Just write m. Minus 2y, excuse me. And the y, the power, the derivative number of y, like the derivative number of this would be 3. The derivative number of just y would be 0. Now just for the record, y squared and that are different. This means y times y. So when you put the power in brackets, it usually means derivative. Since this is a differential equation class, it means derivative. Okay. So the derivative is 0, so we have m to the 0, which is 1. 2 times 1 is 2. And this equals 0. Now, we want to factor this. And if you suffer through it, you'll see that this factors the 2m minus 1 times m plus 2. And how did I get this problem? How did I make it up? Well, to be honest, I randomly wrote this down. I multiplied it out. I had 2m squared plus 4m minus 1m is 3m minus 2. And then, instead of m squared, I wrote double prime. Instead of m, which is understood to be the first, I wrote y prime. And instead of 2, I wrote down 2y equals 0. So I work backwards. So you're going to have to know how to factor. You have to know how to think. You know that 1 minus 1 is 0, but you have to think about that. If this, when to use it. If that times that is 0, then either 2m minus 1 is 0, or n plus 2 is 0. Work on the left one. If that's 1, we're in business. 1 minus 1 is 0. So 2m is 1. Divide by 2, you get a half. Additive inverses. You're adding these two, you're getting 0. So that's plus 2. And it's plus 2 not because of that addition sign, but because 2 is a positive number. So then n must be negative 2. So you'd had m plus a negative 21, then this would have to be, and you're getting 0, then m would have to be plus 21. Okay, so m is equal to negative 2, and once again, we got two real solutions. So, you can write down the general solution. Y is equal to a multiple of e to m1x plus a multiple of e to the m2x. This is m1, this is m sub 2. And you can check it. You can calculate the second derivative of this and then multiply that by 2. And if you calculated the second derivative, you should have the first derivative. Multiply that by 3. And you have y in front of us. Multiply it by 2. And if you add and subtract like it says, you should get 0. Okay, let's try another problem. Suppose you have negative y double prime plus 2y prime minus 1 is 0. So our auxiliary equation will be negative 1 or negative m squared plus 2m. This should be minus 1y, excuse me. Minus 1 is 0. Now, I hate quadratic equations that have a negative value for the coefficient of m squared. I'll multiply both sides by -1. It's not going to change the right side. Multiply by -1. So you'll have m squared minus 2m plus 1 is equal to 0. And all I did was multiply both sides by -1. Now, this quadratic equation, I hope you realize that is factorable. Since there's an understood 1 in the front, I want two numbers that multiply out to 1 that add up to -2. Those numbers are both -1. That is, this equation here is just m minus 1 squared and equals 0. Well, if you square something and you get 0, you have to be squaring 0. 1 times 1 isn't 0, a half times a half isn't 0, 3/4 times 3/4 is not 0. 1 minus 1 might be 0, but 1 times -1 is not 0. m minus 1 must be 0. So m is 1. But here we only have one solution. This is case 2. This is where the discriminant is 0. Just to convince you of that, we have in our case a is 1, b is what m is being multiplied by, which is -2, and c is just 1. So you have -2 squared, which is 4, minus 4 times a, which is 1, times c, which is 1, and this product here is 4. And yep, 4 minus 4 is 0. So we're correct that we got one answer. And we're now ready to write down the solution. The solution when you have 1, the general solution when you just have one root is as follows, to remind you. Y is equal to C1 e to the mx plus C2 times x e to the mx. And our m is 1. So y is C1 e to the 1x, which is x, plus C2x e, again, 1 times x is just x. So there's our solution. There is our solution. One silly comment. Remember here I multiplied by -1. I could have multiplied here by -1, and I would have had y double prime minus 2y prime plus 1y is still 0. And the auxiliary equation would have been 1m squared minus 2m plus 1 equals 0, which is exactly what I got. So you could have multiplied by the -1 a little bit earlier. Now, suppose you have y double prime plus 2y prime plus 2y is equal to 0. Suppose you have that. The auxiliary equation would be 1m squared plus 2m plus 2 equals 0. Here, a is 1, b is what m is being multiplied by, which is positive 2, and c is 2. And b squared minus 4ac, it would be b squared minus 4ac. b is 2, a is 1, c is 2. So you get 4 minus 8, which is -4. Okay, so we're going to have two imaginary roots. Now remember, m is going to be -b plus or minus the square root of b squared minus 4ac all over 2a. And please remember, we just calculated to b squared minus 4ac. So we're going to get negative b, b is 2, negative b, plus or minus the square root of, in our case, negative 4, over 2 times a. So if a is 1, you get 2. You get negative 2 plus or minus. Now, the square root of negative 4 is negative 4 is 4 times negative 1. Now, if both of these numbers are not both negative, that is, none of them are negative or only one is, you can take the square root separately. The square root of 4 I know, the square root of negative 1 I know, it's called I. So we get 2i over 2. Well, negative 2 over 2 is negative 1. Plus or minus 2i over 2 is just 1i. That is, a is negative 1 and b is positive 1. That is, we're getting two complex conjugate roots. Now we know what the general solution is because we memorized it. The general solution is y is equal to e to the ax times c1 cosine bx plus c2 sine bx. And a is negative 1 and b is 1. So y is equal to e to the negative x times c1, c1 cosine of 1 times x is x plus c2 times the sine of 1 times x is x. And there it is. The whole job is to find the alpha and the beta. Let us try another one. Okay, let's consider this problem. Suppose you have 4y double prime plus 4y prime plus 17y equals 0. But you also have initial conditions. Y of 0 is negative 1 and y prime of 0 is good old 2. So basically, we're going to ignore this to the very end. We're going to solve this equation. And we get the auxiliary equation to be 4m squared plus 4n plus 17 equal to 0. And if you actually solve for this, you'd get that m is equal to negative 1 plus or minus the square root of negative 16 over 2, but negative 16 is the same as 16 times negative 1, and only one of these two numbers are negative. So the square root of negative 16, I can think of it as the product of those two square roots. The square root of 16 is 4, the square root of negative 1 is I. You have negative 1 plus or minus 4i over 2. This division, negative a half, plus or minus. That division, 2i. Okay, then this is the A, that's the B. This is the case 3 problem because we got complex roots, and we now know that the general solution is y is equal to e to the ax times c1 times cosine of bx plus c2 times the sine of bx. And that's the solution, the general solution. So we need to find c1 and c2. So I'm gonna bring this up to the top. And notice everything that I just erased, including the steps I didn't include, was just basic algebra, high school algebra type problems. So we know that y is equal to e to the negative 1/2 x times c1 cosine of 2x plus c2 times the sine of 2x. I'm going to go and use the first equation, second. We're going to do the first equation because it's the y equation, and we know what y equals. On one hand, y is 0 is e to the negative 1/2 times 0 times c1 times cosine of 2 times 0 plus c2 times the sine of 2 times 0. And 2 times 0 is 0. Even 1/2 times 0 is 0. So e to the 0 is 1 times what's in the brackets. You don't even have to bother timesing by 1. That's 0 and that's 0. We have c1 cosine of 0 plus c2 times sine of 0. Well, cosine of 0 is 1. c1 times 1, c1. Plus sine of 0 is 0. c2 times 0 is 0. So you just get c1 on one hand using the formula. But on the other hand, they tell us what it is. It's negative 1. Okay, I'm going to the second line on the board, and I'm going to replace c1 with negative 1, or just a negative sign. So I use that equation, this equation, to find c1. I use the other equation to find c2. Once in a while, none of the equations separately will solve for c1 or c2, but combined you can get it. You might get two equations from each of, you might get two equations, you might get an equation from this and an equation from that, and those two equations and two unknowns. Both of these equations from here will have two unknowns. The equation here can have the two unknowns, namely c1 and c2. And you get two equations. Maybe the first equation said this, and the second equation said that. And if you add these, so the first equation that I got from y is 0 is negative 1 is not going to tell me exactly what c1 is. The second equation that I got from y prime of 0 equaling 2, that's not going to help me. But if I say add these, I'll get 2c1. This canceled out is 3. So c1 is 3 over 2. And then I can solve for c2. If you like, you can subtract. This will cancel, but when you subtract those two, you'll get 2c2. And 1 minus 2 is negative 1, so c2 would be negative 1/2. So don't think because you used one equation you must get one solution. In this case, I think you will though. Now, when you take the derivative, sometimes you're going to take the derivative of that term, of that factor, and sometimes you won't. But either way, you're going to have that as one of the factors. So let's use the product rule. The derivative of first, which is negative 1/2 times e to the negative 1/2 x, which I put out in front, times the second factor, negative cosine 2x plus c2 sine 2x, plus the first factor, which is already in front, times the derivative of the second factor, which will be 2 times the sine of 2x. The derivative of this will be negative 2 sine 2x. But when you count the negative or include the negative in front, you're going to get positive 2 sine 2x. Plus, the derivative of this will be 2c2 cosine of 2x. Now, we have like terms floating around here, inside the brackets. How many cosine of 2x's do we have, for example? Well, we have plus a half and 2c2 more. We have 1/2 plus 2c2. That's how many cosine 2x's we have. So I dealt with that and that. Now, how many sine 2x's do we have? Well, we have negative a half c2's plus 2. That is, we have 2 minus a half c2. That's how many cosine x's we have. Now, I plug in the value they tell me to plug in, 0. Y prime at 0 on one hand, a half times 0 is negative a half times 0 is 0. 8 to the 0 is 1. 1 times this is just this. So I'll just plug the 0 in here. I get 1/2 plus 2c2 times cosine of 2 times 0, which is 0, plus 2 minus a half c2 times the sine of 2 times 0, which is 0. Now, the cosine of 0 is, the sine of 0 is 0. So this times 0 is 0. It's not there. Cosine of 0 is 1. This times 1 is just this, plus 0. But it's supposed to equal 2. Now you should know that a half plus 1/2 equals 2. So 2c2 is 1/2. Divide both sides by 2. And the left side is very, very friendly to divide by 2, and you get c2. But you don't want to divide 3/2 by 2. Well, there's an alternative for dividing by 2. You multiply by a half. And when it's friendly to do, you need to do it. So c2 is 3/4. So I come to the second line up here, and instead of c2, I write 3/4. And here is my solution. There it is. Let's write it down a bit neater, and we'll say we're done with this problem. Y is e, just copying this line, is e to negative 1/2 x times, and I hate starting off with negatives, so I'm going to write the 3/4 first. 3/4 sine of 2x minus the cosine of 2x. And there is your solution. 100% accurate, no constant, no unknown. Okay. Now, we'll look at what maybe I'll call special cases. What if you have y double prime plus k squared y equals 0, and y double prime minus k squared y equals 0, where k is a real number. So we'll separate this, and on the left side, the auxiliary equation will be 1m squared plus k squared equal to 0. So m squared is negative k squared. Now, if m squared is anything, I don't care what this is, then m must be plus or minus the square root of the anything. But this anything is, I can think of k squared as negative k squared as k squared times negative 1. And since only one of them is negative, I can take the square roots separately. I know the square root of k squared is k, and the square root of negative 1 is I. So m is plus or minus ki. In particular, it's 0 plus or minus ki. That is, the 0 is the a, and the k is the b. And the solution is always y is equal to e to the ax times cosine bx plus sine bx. So y is going to be e to the 0 times x. Well, 0 times x is 0, and e to the 0 is 1. So I don't even have to write this piece at all. It's just going to be cosine of b is k, cosine of kx plus the sine of kx. That is the solution, and nothing really special there. Nothing special there. Let's look at the other side. The auxiliary equation will be m squared minus k squared is 0. So m squared must be k squared. So m is plus or minus the square root of k squared. There's my plus or minus, and I know the square root of k squared. It's k. The k is actually some positive number, excuse me. Well, even that doesn't have to be true. Okay, so now we have our two solutions. So that's an easy one. Y is equal to C1e to M1x kx plus C2e to M2x. And we have that. So now we can have a little fun with this. How about we let C1 equal 1/2 and C2 is negative 1/2. Now what will this become? So y will then become e to the kx plus e to the negative kx all over 2. The reason this is neat is because that's cosh of kx. Now, what if alternatively I let C1 equal C2 equal 1/2? That is, C1 and C2 are both the half. And I'm going to come right back here, like general equation. So y will equal to e to the kx plus, okay, excuse me, I made a silly mistake. In my first case, I let C1 and C2 both be 1/2. Now, I'll do what I meant to do initially. C1 is 1/2 and C2 is negative 1/2. So that's just going to make a negative 1/2 all over 2. But that's the sinh of x. Sorry, that's the sinh of kx. That's the sinh of kx. The one above is the cosh of kx. The hyperbolic cosine of kx on top, the hyperbolic sine of kx on the bottom. So what we can say then is that a general solution will be a linear combination of these. That is, y can be a multiple of cosh of kx plus a multiple of the sinh of kx. And what's neat about this is it looks just like this one. Oops, do have a little error here, sorry. I should be saying C1 plus C2. Okay, I should be saying C1 plus C2. Y is C1 times well, actually there should be a C1 here, and before the sign is C2. Sorry about that typo. C2. So we have C1 cosine of bx plus C2 sine of bx. And that's what y equals. Take a linear combination of them. Now, these two look very similar, except this one has the hyperbolic. That is, if I erase h, they're exactly the same answer. And of course I have yet another silly error. It's not an error, it's just incomplete. Like I wrote here, b is k. So y should be c1 cosine of kx plus c2 times sine of kx. Now, this bottom equation I just boxed, and this one over here that I'm boxing, they look very similar except for the hyperbolic function. And they both came from this. I just felt it'd be fun to throw that in. Now up to now, we've only dealt with second order homogeneous linear equations with constant coefficients. Let's look at a third order. Third order differential equation. Y triple prime plus 3y double prime minus 4y is equal to 0. So it's going to be m is the third derivative plus 3m, it's the second derivative, so I put 2. Just be mature enough to realize that's the zeroth derivative. Doesn't be minus 4 times n to the 0, which is just minus 4. This is 0. Now, how you should start these problems is you should look at the coefficients. You have 1, 3, and negative 4. How do you get 0? Well, you want to have plus 1 plus 3, that's 4. Take away 4 is 0. So I want this to be 1, and there's my plus sign, so there's my plus. So I want this to be 3, and there's no problem getting this to be negative 4. Well, if I let n be 1, this will be 1, this will be 3, 1 plus 3 is 4, take away 4 is 0. This is textbook mathematics. They rig it so it's somewhat simple, so you can see it by inspection. So, one solution is m equals 1. Now, you can do long division or synthetic division to find the other roots. I'll use synthetic division. I put the 1 out here, and then a bar. And I have one, I'm reading from here. I have 1m cubed, 3m squared, no m's, the constant is -4. I like to put a 1 here, or a 0 there. And you add, you get 1. You multiply, you put the answer there. You add the 3 and the 1, you get 4. You multiply, 1 times 4 is 4. The answer goes there. You add 0 and 4, you multiply, 1 times 4 is 4, you put the answer there, and when you add you get 0. That's your check. Isolate the 0. Your equation started from a cubic, so it goes down to a square. It's 1m squared, 4 is positive, plus 4m plus 4. So now I know that when I factor this equation, I know one factor is m minus a solution, which was 1, times what I have down there, m squared plus 4m plus 4. And like it says, it still equals 0. So I have m minus 1, and I would love to factor that. Since there's a 1 understood in front of the m squared, I like two numbers that multiply out the 4 and add up the 4. The two numbers are 2 and 2. They add up to 4, they multiply out the 4. So it's going to be m plus 2 times another m plus 2. That is m plus 2 squared. So one solution is when this is 0, which happens when m is 1. Another solution is when this is 0. But there's not too many numbers to square to get 0. There's only one answer. It's 0. That is, this must be 0. And that's when m is -2. Okay. So we have the 3 solutions. It was a cubic equation. This had, that root, -2, had multiplicity of 2. And that's going to be important. So we now know that y is equal to e to the, is a multiple, c1 that is. It's c1 times e to the mx plus c2 e to the nx. But since this had multiplicity of 2, we have plus c3 times x e to the nx. And that is your general solution. Let's try another one. Suppose you have y cubed, y triple prime minus 4y double prime minus 5y prime is 0. So you get m cubed minus 4m squared minus 5 equals 0. Since there's a 1, so this is a cubic. And since this is first derivative, I should have m. Now, yeah, it is a 1 in front, so let's not worry about it yet. All of these terms have an m in them. I can factor it out. M times m squared gives me that. M times -4m gives me that term. And m times -5 gives me -5m. And that's 0. Now we're not going to lose this m way in front, but the m squared inside the bracket, its coefficient is 1. So I'm going to try to play the m followed by a number game, times m followed by another number. We want two numbers that multiply out to -5, constant, but add up to the coefficient of m. And the two numbers are -5 and +1. equals 0. So either m is 0, and that happens when m is 0, or m minus 5 is 0, or 5 minus 5 is 0. That is, m must be 5. And if m plus 1 is 0, m is negative 1. Those are the three answers. Okay, and they're all multiplicity of 1. How do I know that? Because the powers are all 1. So y is going to be c1e to the 0x, that's 0, plus c2e to the 5x, plus c3e to the negative 1x. Now, 0 times x is 0, and e to the 0 is 1. So this is 1. Well, c1 times 1 is c1, plus c2e to the 5x, plus c3e to the, you can say negative 1 times x is just negative x. Personally, that's what I would write. And there is a solution to a third degree differential equation of the type that we are working on. Okay, try a couple more. Suppose you have y triple prime minus 5y double prime plus 3y prime plus 9y equals 0. So we have 1m cubed minus 5m squared plus 3m plus 9 equals 0. So you want to look at these coefficients, 1, 5, 3, 9. And you want them to give 0. And I notice, oh, look at this. If I add the first three numbers, I get 9. And if I take away 9, I'll have 0. And just for the record, you can add 9 to everything else that'll be negative 9. So I could have a minus in front. I is the way I get 0. Now, since I do have plus 9, maybe I never should have even looked at that case. So I would love this to be negative 1. I already have my minus here, so I like that to be 5. And I like this to be negative 3. Just let m be negative 1. If m is negative 1, that'll be negative 1. That minus is that minus. Now, negative 1 squared will be 1. Times the 5 in front will be 5. And positive 3 times negative 1 is negative 3. And when you add 9, you say, yeah, I'm getting 0. Okay, so now we know that m equals negative 1 is the solution. Let me write it here. M equals negative 1 is a root or a solution. So I know that when I factor this, when I factor m cubed minus 5m squared plus 3m plus 9, I know that m minus that number, that is known as m plus 1, will be one factor. I'm going to find the other factor right now. And then, most probably, I'll have to factor that one. So I know that negative 1s are root or solution. So I put negative 1 here. We're going to do synthetic division. And I come here. I have 1m cubed minus 5m squared, 3m's, and a constant is 0. My style, I like to put a 0 here. I add the 1 and the 0, I get my answer. I multiply, and I put my answer there. I add the negative 5 and the negative 1, get negative 6. I multiply, I get positive 6, I put my answer there. I add the 3 and the 6, I get 9. I multiply it by the -1. I put my answer there, which is -9. When I add those two numbers, I get 0, which is good. That means I did everything right. Now, since I'm starting off with a cubic, and I'm only pulling out a linear factor, then it's going to go down 1 degree. It's going to be 1m squared minus 6m plus 9. M squared minus 6m plus 9. And this is supposed to equal 0. I mean, after all, it said that. Okay, well, m plus 1 I can't factor, but can I factor this? Since there's an understood 1 in front of the m squared, I'll play the m followed by a number game. The two numbers should multiply out to 9, the constant, and add up to the number in front of the m. The two numbers happen to be the same. They both happen to be -3. When you multiply -3 and -3, you do get 9, and when you add them, you do get -6. So we have n plus 1 times m minus 3 squared. So either this or that is 0. What plus 1 is 0? -1. Here, m is 3. But it had multiplicity of 2. That's somewhat important. So now we're ready to write down the general solution. General solution. Y is equal to c1e to the -1x plus c2e to the 3x. But since 3 came up twice, we'll have c3x to the 3x. And there is the general solution to this differential equation. Since there are 3 unknowns, they would have to give you 3 points on this equation so you can solve for C1, C2, and C3. They'd have to say, for 3 pieces of information, they'd have to say something like y of 0 is 2. They can also give you y of 10 is 3, and y of -1 is 4. Or they could have said y of 0 is 2, y double prime of 10 is 3, and y triple prime of -1 is 4. They have to give you 3 pieces of information, and then, as long as they're not contradictory, you could get a particular solution. You could solve for the exact solution. You can solve for C1, C2, and the number C3. Okay, let us try one last problem and then we'll be done with this. Okay, so suppose you were told that the fourth derivative of y plus 2 times the second derivative of y plus y itself is 0. And they tell you solve this. So you're going to get m to the fourth plus 2m squared plus 1 is 0. Now, whether you like it or not, or believe it or not, this is a quadratic equation. Because if I let, for example, u equal m squared, well, that would mean if I square the left side, I get u squared. If I square the right side, I get m to the fourth. And equal, it means another way of saying this is that. Another way of saying m squared is u. Another way of saying m to the fourth is u squared. Another way of saying m to the fourth is u squared. Plus is plus, 2 is 2. Another way of saying m squared is u plus 1 equals, and then the number 0. Now, it turns out that the left side is a perfect square. Two numbers that multiply out to 1 but add up to 2 are 1. Just u plus 1 squared is 0. Okay, so we factored it. But remember, u is really m squared. U is really m squared. So we have m squared plus 1 squared is 0. Well, then there's no way out of it. I don't care what's inside those brackets. It must equal 0. So then m squared must equal negative 1. M squared is negative 1. And if you square something and you're getting this, I don't care what that is, then what you're squaring, namely the m, is plus or minus the square root of this. So there's my plus and minus. The square root of negative 1 is I. The m is plus or minus I. That is, m is 0 plus or minus 1i. Let me write that here. M is 0 plus or minus 1i. The 0 is your A, and the 1 is your B. Okay, wonderful. Okay, so we know that y is equal to e to the ax times c1 cosine bx plus c2 sine of bx. So y is equal to e to the 0x times c1 times cosine of 1x plus c2 times the sine of 1x. Clean it up a little bit. 0 times x is 0, and e to the 0 is 1. So it's 1 times this, which is just that. So y is just that. It's c1 times cosine of 1 times x is x plus c2 times 1x is x. There is your solution to this fourth degree equation. With one little mistake. The multiplicity is 2. I'm going to think about that for a moment. Now that's not true. If it said that m squared was equal to 0, then I would say it had multiplicity 2, or if 0, that would mean m is 0. So 0 would have multiplicity 2. If it said m minus 5 squared was 0, then m would be 5 with multiplicity 2. But it doesn't say that this equation is being raised to any power to get 0. Oops. Yes, it does. It says it right here. It says it right here, which means it has multiplicity of 2. Each of these answers that I have at the far bottom left, each of those answers, 0 plus 1i and 0 minus 1i. They have multiplicity of 2. They have multiplicity of 2. Okay, so why don't we just get rid of this right here? And we'll kind of reinvent the wheel a little bit. So let's even just use the last line we see now. So we have two answers. So y, 2 roots, is equal to c1 e to the negative ix. But since it has multiplicity of 2, I'll have plus c2 times x e to the ix, negative ix. And then I have, that used the negative I. Now I'll use the plus I. So c3e to the ix, it had multiplicity of 2. So I get c4e to the c4xe to the ix. So here is a general solution to our equation. Now, let's see how we can clean this up a little bit. We know that e to the ix is cosine x plus I sine x, and that e to the negative ix is cosine x minus I sine x. Okay. So then that here is similar to this. This and that. Okay, without the coefficient. It's similar to that. Okay, that is what I just underlined is let me say C1 first. It's C1 e to the negative ix, which is this, plus C3 e to the ix, which is C3 times that. Okay, that is this plus this. What I meant to say is exactly that. Exactly that. Okay. But we want to write it a little bit differently. C1 times this. I can write this as this equation here. Cosine x minus I times sine x. Plus C3 times e to the ix, which I write that way. Cosine x plus I sine x. Okay, now let's combine like terms. I have C1 cosine x plus C3 cosine x. I have C1 plus C3 cosine x. Plus, now let's add sine x's. I sine x. How many I times sine x's do I have? Well, I have C3 of them, and I'm taking away C1 of them. Now, this is nothing more than, I'll just call that C1. C1 cosine x plus, big C1. And I'll call that big C2. plus big C2 I sine x. That's what these two add up to. That's what those two add up to. So I have C1 cosine x plus C2I sine x. Now, what will these two add up to? Well, they're very similar. Maybe here I have C2 and here I have C4. But they also have an x. The thing is I can factor out the x. I can factor out the x. So I have x times C2 e to the negative ix plus C4 e to the ix. I can factor out the x. And then I play the same game. I play the same game. I have the x factored all the way out. And then I have C2 times e to the ix. So this just becomes C2, and that's e to the ix, plus C4, that is what it says, times e to the ix. But what's in the bracket is e to the ix. So then you just factor a little bit. The x is still way out in front, or I should say distribute. How many cosine x's do you have? Well, you have C2 plus C4. That's how many cosine x's you have. How many I sine x's do you have? How many I sine x's do you have? I times sine x. How many you have? Well, you have negative C2. I'll write that second. And you have plus C4. Now, I'll just call this, so there's the x. I'll just call that C3. C3 cosine x plus, I'll call that C4. You want to use different coefficients, go for it. So, if I can come down to the far left, bottom left, and I'm going to concentrate right up here. I had my general solution to be this sum, the sum of those four terms. And I rewrote the sum of those two right underneath. It was C1 cosine x plus C2I sine x plus these two, which I did on the bottom, plus x times C3 cosine x plus C4I sine x. Okay, now we talked about coefficients. We talked about constants. C2 times I is just a constant. C4 times I is just a constant. The constants are going to factor out when you take derivatives and even when you don't take derivatives. So since it still equals 0, you're going to end up with I times something else. And it will be 0. You want to know why? Because what's in that bracket will be 0. That is, you didn't need the I. You can have C1 cosine x plus C2 without the I sine x plus x times C3 cosine x plus x times, x is factored out, plus C4 sine x. You do not need that I. And here is your solution. That one was a bit much. That's why I put it last. This finishes the section on homogeneous linear equations with constant coefficients. Work out some examples and not that bad, especially the easier ones.